All right, I just want to show a little video that will get us or transfer us from the concept you saw in last lesson about this slopes of secants and approaching tangents from either side. And we're just going to introduce the mathematical equivalent of this that was discovered by Newton. The Jensen site refers to it as Newton's quotient. It's also known as the first principles version or calculation of what's called the derivative, which is really the slope of this tangent or the instantaneous slope. So it's going to go at Jensen here briefly for you. So it's this one here, Newton's quotient, that I'm introducing. In the lesson, he does some more complicated functions than many might start out with. So I just want to show you a sort of a simpler version, and then you can see how it works for more complicated versions as well. So the idea is from the previous lesson, hopefully you're good with it from the previous lesson, that on this side, we could calculate a slope here, and I'll do that on the Smart Notebook file actually. So just to establish the main concept, we've got slope of the line and out. So this secant from A to B. There's a calculation there. You have your delta x and your delta y, so change in the x and change in the y, and obviously the slope here the computer calculated to be 3. Well, that would come from slope delta y over delta x. And so in this case here, we could do all sorts of calculations for this, but for example, this is just like x squared, right? And so if we're looking at 2, we've got a point that is an x value of 2, and then of course the x squared is 2 squared. So you can see that this is the point 2, 4. And down here it's at 1, and so this point is 1, and 1 squared is 1. So 1. But the result here then is a change in the y. So you get basically y2 minus y1, x2 minus x1, and you go up to grade 9. So we've got the y2 value of 4, take away the initial y value of 1, and we're looking at the x value of 2. So we end up at over here, in which when we started at. So we get 3 divided by 1, which is of course 3, right? It's the main underlying principle here to do with the slope. The next level stuff starts or comes in on the last lesson you saw, which is this idea here where we can approach this, the B value. So the A point and the B point can get closer and closer together. And so we're approaching the instantaneous slope at x equals 1 as we get closer and closer, and see how the value went from 3 up here to closer and closer. You know, as closer I get here, see how it's going to stop changing as much. It's like really getting close to 2, right? If I went from the other side, you can see we started our slope of, think of slope of 0, and it's changing a lot. As we get closer and closer and closer, it starts to change less and less. So it's approaching, when you look at the table of values, like in yesterday's lesson, you can see the numbers are just changing by less and less as you go closer and closer. And so you can see it's approaching 2 from the left side, it's approaching 2 from the right side. And so you can confidently say that it's approaching 2 overall. So it allows us from the table of values to talk about the slope at that instant being 2. The problem, of course, is that if you really want to look at the slope of the tangent itself, let's make a picture of that for the book lesson. So the issue is, bear with me for a second here. If we wanted to talk about that slope of 2 at that instant, what we're really looking at mathematically is delta y over x again. And we have a delta y value, whatever number. Basically, actually, they're both ending up being 0, right? If we're approaching that spot here, or A and B at the exact same spot. So we have this like 0 over 0. Call it a indeterminate or a discontinuity in the calculations to do with it, but it's a problem, right? It's a mathematical problem that was sort of realized at some point, and they said, okay, well, we have to have a way to deal with this. So what they did is they formalized, so Newton formalized a way to sort of calculate this. And it looks like this to start out with. So this is slope, and then this is instantaneous rate of change. Slope of a tangent, right? I'm going to show you the formula, and it refers to as Newton's quotient, which is the first principles version of getting this, right? Getting this instantaneous rate of change, the slope of the tangent, which is also going to be called the derivative. So that is equal to, okay, the notation is the limit as h goes to 0 of f of x plus h minus f of x all over, in this case, on h in the bottom. Right? So what we're doing is we're looking at, I'm just going to copy this picture right here. Paste it in small here. We're picturing the h value being this, the amount that we're going over. That's our delta x, right? So if this is h, then you can see up here you have, this is x, whatever x value you're talking about, and then we go over h, and so this becomes x plus h, right? And then this is, the height here is the value at x, and the height here is the value at f of x plus h, right? So if you think about this formula here, it's really equal to, it's really equal to a delta y over a delta x. Because it's the y2 minus the y1, and then this is the result of doing x2, which is really x plus h. Let's do that better. X plus h minus the initial value of x, right? So x2 and x1. So when you do that, of course, the x's just cancel out, and you're left with just h. Right? So this thing, even though it looks kind of weird, really actually delta y over delta x. The process that we look at is we actually formalize the idea of saying, okay, well, what happens as that thing approaches a smaller interval, and you zone in on an instantaneous rate of change. And so by making h go to 0, that brings us from average rate of change, which this technically would be, right? This would be average rate of change, ROC for short. And then this makes the average rate of change. So average rate of change approach the instantaneous rate of change, which is often shown as AROC and IROC, right? AROC for average rate of change, instantaneous rate of change. So that's what it looks like as a concept. And that needs to be something that's just kind of intuitive. When you look at it, you get what it means. The next step is to use it algebraically. I'm going to show you a simple example. So it's going to be this x squared example. So we've got function x equals x squared. And we're saying, okay, well, the instantaneous rate of change, the slope of a tangent, the derivative, all these different words that we're going to throw around, right, equals the limit as h goes to 0 of f at x plus h minus x h. I'll show you what happens, and then we'll confirm the value that we saw here, that it should be 2, right? That's our goal or hope. So it looks like this. So we'll keep this limit idea. We haven't done it yet, right? Eventually we'll do that limit and it'll disappear. But f at x plus h means, well, f at x is x squared, right? So we'll put in x plus h in there. So this means to do x plus h squared. And then take away f at x, so that's just x squared. Right, just an x plugged into x squared. And we're still over h. So limit is h goes to 0, still there. X plus h squared, either you do it off the side where you're like x plus h, x plus h, and you multiply it all out. So you have this and this, this and this, and you have your x squared plus your xh plus another xh plus their h squared. But really, most people at this level would just say, oh, that's equal to x squared plus 2xh plus h squared. And so that part right there, including the square, right, is this part, just to be obvious. I'll code things a little. And then we have a take away x squared. I just want to show you this nice easy example because it's much easier to see how simple this really is, and then it just gets more complicated in terms of this multiplication that we have to do is where things get more complicated. But really the main concept is still pretty simple. So what we get next here is we notice that basically always any part without an h goes away. So x squared take away x squared goes away. So we are left with limit h goes to 0 of just 2xh plus h squared all over h. Okay, and this is the step you're always waiting for when you do these first principle calculations of the instantaneous rate of change with the slope of the tangent, i.e. you're really doing is the derivative. I'm going to show you eventually here the trick that the derivative result is. But you can factor out, you can common factor out an h, because there's an h in common, and so you can end up with an h out front. Like that. So this is where things happen, where you can say, okay, we get rid of the h on the top and the bottom. So we really get rid of that 0 over 0 before it happens. It's kind of seems like a trick almost, right? But at this stage here, when you say, okay, let's let this happen, we're going to make it actually happen. So this just becomes a 0. So once we put a 0 in there, we say, oh, okay, so this thing, the limit is really just 2x, right? So the average rate of change, or the instantaneous rate of change, the average rate of change approaches the instantaneous rate of change, and it's really just 2x. Well, in our case, in the geometry sketch pad thing that I showed you there, we're looking at an x value of 1, right? So let's say here, x equal to 1. The slope of the instantaneous rate, or the instantaneous rate of change, or the slope of the tangent, and so on, would be, so the tangent slope, I'll just say, tangent slope at x equals 1 is, of course, this. It's equal to 2 times 1, which is 2. We said it should be based on the computer calculated. And you can see the same thing in the previous lab. Your table of values approaching, 1.99 and 2.001, from the left side, right side perspective. So you can see that works. Okay, so this mathematical process gives us that slope of the tangent without having to do a big table of values and see the idea of approaching from left and right. But it's all possible because of that table. Keep that in mind. But this process kind of does it for you, right? So we got that. If we had another equation similar to this, if we had a 3x squared, do that one. Let's do 3x squared. Not really any harder algebraically, right? So the instantaneous rate of change, the tangent, in other words, is our limit. H goes to 0. H minus x all over h. So really that's really make sure you realize that's just a slope, right? That's just a delta y over delta x. And then really as delta x goes to 0. So we're getting your average rate of change becoming your instantaneous rate of change. Just want to remind you of that. It needs to be obvious, right? This is really just delta y, y2 minus y1. So it is delta y. And the same thing for this one. That's your delta x. So this one here, the math, extremely similar. But it's just part of noticing the pattern to give the derivative trick result. So we have a 3 times an x plus h squared and minus a 3 times an x squared. just function, right? That's plugged in. Always will be. So when this h goes to 0, this is just going to be 3 times the x squared plus the 2xh plus the h squared, and take away the 3x squared. And so that's going to give us, as h goes to 0, we're going to have a 3x squared. We're going to have a 6xh, right? We're going to just multiply on each part, and a 3h squared, x squared. And like I said, as always, the part without an h goes away. That's the magic you're always waiting to happen. Like if in questions where it's more complicated, it's just way more terms. And so you're just waiting to see what all the terms that cancel out and leave you with something that has an h everywhere. So in this case, it looks like this. And you could even at this stage say, okay, the h divides in here once, h divides in there, and so on, and end up with directly here, the limit as h goes to 0, supposed to say limit, where we have 6x, 3, right? So 3h. I was like, wait a minute. So that goes to 0 means that goes to 0, and that means we're left with just 6x. Right? So we had the function 3x squared, then slope at any spot, we keep that, right? This is the change. The change is 6x, and so the slope of the tangent at 1, if you want to pick on that same spot again, would be 6 times 1. So it'd be 6. So let's go to the sketchpad file. See that would be true. Okay, so let's just change this thing to be 3x squared equals, and boom, there it is. There's our 6 that it calculates for us just based on actual just calculating numbers, right? No fancy first principles or anything like that. Where's my notebook file? There it is. So let's grab a picture of that to confirm that thing. So many things open here. And that's just basically saying, yay, it worked, right? So in the lesson, we'll go over the idea of this again. I hope the repetition helps make it seem really obvious. The examples he does are f of x equals order x squared minus x plus 1. He finds that the resulting slope, we need to do something actually just before we get to that stage here. I'm just going to give you the notation to do with this. I mentioned the word, right? So this process here is referred to as first principles. Principles process, this first principles way of getting the slope of the tangent. Okay, so determining instantaneous rate of change. The other thing I want to mention is if we're talking about a function, like if this was, we're talking about f of x, right? Well, then this is f prime of x. Okay, so it looks like this, or I'm going to label this here. This thing is equal to first principles, and it's equal to f prime x is the notation, so the little apostrophe. Okay, so back here would have been good if I had said like really it's this.
Unfortunately, today's basketball games have been canceled. There was transportation problems for PCI. There will be practice in basketball teams, but the games have been canceled for after school. And following the bell, would the time to raise it is the Parker Police Company office.
So our results, let's start with the mine first, we have that, and then it led to a first principle derivative instantaneous rate of change slope of a tangent. All different ways of saying it, result of 2x. That's what x equals 3x squared. It put 3 in a purpose so you can see what's going on. That's the second derivative, that's later on. First derivative instantaneous rate of change ended up being 6x. The results from the Jensen lesson you're going to see after this would be, I can just tell by looking at it, but I have a note from what it was as well. 1/2 x squared minus 1. And the other one we did was just x squared minus 5x plus 4. And there's a pattern, recognizable pattern of this that was noticed by Newton. And so it was all formalized. There's another that as well. Show the better names. I don't know, I forgot. Leibniz is the guy. So who the hell? That one, anybody that knows about this process would notice that process would, result would give you this. So take a look at that and see if you can start to notice like the derivative trick. I'll just leave that with you. Technically part of this course, but still good to nice little show, right? It's kind of actually a spoiler alert for calculus, because calculus you do the first principles thing a lot, way more than this class is just talking about it because it relates so much to what we're doing. There and 9 there. But the trick result is just kind of too neat not to show it. So go ahead and watch the Jensen video as well. You'll see the calculations with more complicated versions. Picture, trying to do this process here with more and more complicated functions. This is obviously, it explodes, it gets bigger and uglier. But eventually, if you do it right, all of the parts of H cancel out, giving you a nice simple equation for the instantaneous rate of change. So it's a pretty powerful concept. I'm going to leave that with you for the trick. Let me know if you have any questions.